previous sessions, we have discussed the order properties as well as algebraic properties of R. So, welcome to the 7th session of real analysis, in which we will be discussing more about how problem solving can be done using the algebraic properties and order properties of real numbers. In this session, we will be learning more about the inequalities and how to find the solutions of inequalities. So, let us do first a problem. Determine the set A of real numbers x such that 3x plus 4 is less than or equal to 10. So, we are given a set x which are real numbers which satisfies the condition 3x plus 4 less than or equal to 10. So, first we will take the condition given 3x plus 4 is less than or equal to 10. This can be rewritten as 3x plus 4 minus 4 is less than or equal to 10 minus 4, because we have seen in the previous session, if A is less than or equal to B, A plus C is less than or equal to B plus C. Therefore, we can subtract 4 from both the sides of the inequality. The inequality remains exactly the same. So, that is same as 3x is less than or equal to 6, or which simplifies to give x less than or equal to 2. So, this method is used in linear programming problems and so on, and in different other branches of mathematics as well, where we have to find the solutions of inequalities, linear inequalities we can say. So, drawing on the corresponding graph of 3x plus 4 is equal to 10, or we have 3x is equal to 6, or suppose we draw the graph of y equal to 3x minus 6 as a straight line, we will be getting the graph something like this. The x intercept being, this is 1, 2, 3 and so on. Here you have 1, negative 2, negative 3, etc. Somewhere here you have your negative 6. So, that if we put x equal to 0, we will be getting y equal to negative 6, and y equal to 0 gives x equal to 3x minus 6 is equal to 0. Solving, we get x is equal to 2. So, we are getting 0 comma negative 6 as one point and 2 comma 0 as another point on the line. So, this is one point on the line, this is another point on the line. So, we can draw a straight line joining these 2 points because it is a linear function. So, we will be having this going to infinity, this is going to minus infinity on this direction, and this goes to plus infinity on the other direction. So, look at the graph and see for what values of x is this 3x minus 3x plus 4 less than or equal to 10. So, 3x plus 4 less than or equal to 10 means your y should be less than 0. This is less than 0. So, look at the graph and look at those values of x for which we have y values to be less than 0, which means exactly starting from this point downwards we have all the y values. So, that means this side of the x axis gives the corresponding y values to be negative, and that is exactly what we have got by solving this condition, x is less than or equal to 2. So, that is how we solve linear inequalities using order properties of R. Let us look at another example where we are given the set A is equal to the set of all x belonging to R such that x square plus x is greater than 2. So, let us see how we can solve this or how we can find the set of all real numbers x which satisfies the condition, given condition x belongs to R such that x square plus x is given to be greater than 2. So, again as we have done in the previous case, we start with the inequality given x square plus x minus 2 is greater than 0. So, this is a quadratic expression on the left side, and we know that a quadratic expression can be written as the product of two linear terms. So, solving this into factorizing this term, we have sum equal to plus 1, product is equal to negative 2. So, x plus 2 into x minus 1 is greater than 0. And we have seen in the previous session or previous class that if you have a b greater than 0, this implies a is greater than 0 and b is greater than 0, or a is less than 0 and b is less than 0. So, using this result, what we are going to do here is, this implies x plus 2 is greater than 0 and at the same time x minus 1 is greater than 0, or we have the condition that x plus 2 is less than 0 and at the same time x minus 1 should be less than 0. Okay. Now, let us take the help of geometry to understand where these x values lie on the entire real line. So, we will take the entire real line. We have 1 here, we have negative 2 here. Why we are taking 1 and negative 2? Because we need x plus 2 to be positive, x minus 1 to be positive, or x plus 2 to be negative and x minus 1 to be negative. So, x plus 2 is positive means x is greater than negative 2. So, that means we will be drawing negative 2 and 1 here, somewhere here you have your 0. So, x plus 2 is positive means x is greater than negative 2. So, that is the first condition. X plus 2 greater than 0 means x is greater than negative 2, and x is greater than 1 means we have x is greater than 1 towards this side. So, and means it is intersection of the two sets. So, where is both the result satisfied? That means where is x greater than negative 2 as well as x is greater than 1? That is this region. So, we consider the solution as x is greater than 1. For the combined values, x is greater than negative 2 and x is greater than 1, we are writing x is greater than 1. That is enough because here there is an and. Similarly, the next result is for what value of x? Is x plus 2 less than 0 and x minus 1 less than 0. So, we can see x is less than negative 2 as well as x is less than 1. So, where is both the conditions satisfied? Where x is less than negative 2. So, x is less than negative 2 and x is less than 1 indicates that we have to take the common region x is less than negative 2. Therefore, the final solution is the set of all x values which satisfies the condition x square plus x is greater than 2 is equal to the set of all elements real numbers which are greater than 1 That means we have 1 up to infinity, because it consists of all the real numbers which are greater than 1, and because it is only greater than, we can have an open interval here. Union, because it is an OR, this condition or x is less than minus 2. So, whenever OR comes, you will take the union. So, union x is less than negative 2. So, the set of all real numbers which are towards the left side of negative 2 means it is starting from minus infinity up to negative 2, excluding negative 2, because when x is equal to negative 2, this here it will become equal to 2. So, this is the final solution that was required in the problem. Okay. So, that is the solution of this problem. Then we can look at the third question. Determine the set A is equal to the set of all x in R, or the set of all real numbers, for which 2x plus 1 upon x plus 2 is less than 1. So, that also we can solve by a similar method. We are given the third question. We are given the set of all x belonging to R such that, what was the question? 2x plus 1 upon x plus 2 is less than 1. 2x plus 1 upon x plus 2 is less than 1. So, consider 2x plus 1 upon x plus 2 minus 1. So, taking the LCM and solving it, what we get is 2x plus 1 minus of x plus 2 whole by x plus 2, and this is required to be less than 0 in order to satisfy this inequality. So, this is less than 0, and when is that less than 0? Simplifying the numerator, you have x minus 1 upon x plus 2 is negative. So, this can also be considered as the product of two numbers, two real numbers, x minus 1 and 1 upon x plus 2. And we have learned in the previous session that AB is less than 0 if either A is greater than 0 and B is less than 0, or A is less than 0 and B is greater than 0. So, depending upon those two conditions, we have, this indicates that either x minus 1 is less than 0 and x plus 2 is greater than 0, or we have x minus 1 greater than 0 and at the same time x plus 2 is less than 0. So, these two are the conditions corresponding to this inequality. So, x minus 1 is less than 0 means x minus 1 is less than 0 and x plus 2 is greater than 0 means, if we draw the real line, we consider 1 and negative 2 as we have done in the previous case, and somewhere here you have your 0. X minus 1 is less than 0 means x is less than 1. So, x is lying towards the left side of 1, and x plus 2 greater than 0 means x is greater than 2. So, towards this side. So, which is that interval satisfying both? We have the open interval negative 2 up to 1. So, that is the open interval. Now, take the second case, that means x minus 1 is positive and at the same time x plus 2 is negative. But when we do this one, what we have is, somewhere here you have your negative 2. So, x minus 1 is greater than 0 means x is greater than 1. So, x goes to this side, and x plus 2 is less than 0 means x goes to this side. So, we can see that there is no intersecting region or there is no common points which satisfies both these conditions. So, this leads to a null set, actually empty set. So, the solution is, therefore, the solution is only the open interval -2 up to 1. So, we do not have any unions here, you have only one part satisfying the required inequality. So, that is the solution of the third problem. Now, let us move on to the inequalities, standard inequalities which are satisfied by any real numbers. So, the first inequality saying if A is non-negative and B is also non-negative, A less than B implies and implied by A square is less than B square if and only if square root of A is less than square root of B. So, we are given the two conditions that A and B are non-negative. So, suppose A and B are both equal to 0, then we have all these values equal to 0. So, there is nothing to prove. So, without loss of generality, we can prove this inequality in the case of positive real numbers A and B. So, suppose we are given the condition A is less than B, what we have to prove is A square is less than B square and vice versa. That is, we first suppose A square is less than B square and then we will prove that A is less than B. So, let us look at the proof. Inequality 1. Given A is less than B. So, what does this indicate? A minus B is less than 0 or B minus A is greater than 0. Also, we are given A is greater than 0 as well as B is greater than 0, because we have already discussed the case when both A and B are zeros, we have nothing to prove. So, we consider without loss of generality that A is positive and B is also positive. So, by the definition of positive real numbers, we have seen if A and B are both belonging to P, A plus B also belongs to P. Therefore, A plus B is also greater than 0. So, we have now B minus A to be element of P, B plus A is also an element of P. Therefore, B minus A belongs to P and B plus A belongs to P indicates that the product of these two also belongs to P by the definition of P. So, B minus A into B plus A belongs to P. And what does this indicate? The product of B minus A and B plus A is nothing but B square minus A square. You have studied in school. It is an equation we have studied in standard equation we have studied in school. Identity we will say B minus A into B plus A is equal to B square minus A square. So, that belongs to P. And what does that indicate? B square minus A square is greater than 0. So, this implies B square is greater than A square or same as A square is less than B square as we wanted to prove, which was the required result. Now, conversely, suppose that A square is less than B square, then we will simply retract, simply we will go back. So, we have B square minus A square to be an element of P, which indicates that B minus A into B plus A is greater than 0, and we have studied a result. If the product of two real numbers is positive, what does it indicate? Either both are positive or both are negative. But here we cannot have both to be negative. Why? Because we are given A is greater than 0 and B is greater than 0. So, this part will definitely be positive. So, this surely indicates that B minus A is greater than 0. So, what does that imply? A is less than B. So, we have proved the if and only if condition. The next segment, that is square root of A is less than square root of B, is very simple because we have root A to be root A the whole square and B to be root B the whole square. So, because we have proved this part, replacing your A by root A and B by root B, we can simply prove the other inequality as well. So, that is already done in the first case itself. I will explain once more. Square root of A the whole square is nothing but A and square root of B the whole square is nothing but B, and since we have already proved this part as an if and only if condition, this side automatically holds. So, that is the proof. So, that completes the proof of inequality number 1. Moving on to inequality number 2, which is known as the famous arithmetic geometric mean inequality, where we have square root of AB is less than or equal to half of A plus B. So, let us look at the proof of this result. We have what we require to prove is inequality number 2. Square root of AB is less than or equal to half of A plus B, where the identity or equality holds if and only if both A and B are same. So, first let us see what happens when both A and B are equal. So, this proof goes like this. If A equal to B, the LHS is equal to square root of A square, which is nothing but A, and RHS is equal to half of A plus A, which is equal to half into 2A, which is also equal to A. Therefore, LHS is equal to RHS. So, if A and B are same, then it is an equality that we are getting. So, let us suppose the case when A is not equal to B. So, second case, when A is not equal to B, then what happens? Either A minus B is greater than 0 or A minus B is less than 0. From where does this follow? From the law of trichotomy that we have learned in the previous session. So, if A minus B is not equal to 0, either of these two conditions hold, and we have learned in the previous inequality, if A minus B is greater than 0, square root of A minus square root of B is greater than 0, or square root of A minus square root of B is less than 0. But whatever it be, for an real number A, we have learned the square of any real number, non-zero real number, is always positive. So, the square of any non-zero real number is always positive gives root A minus root B the whole square is greater than 0 in both the cases, whatever be the case. So, expanding this using our identity of A minus B the whole square that we have learned in school, we have A plus B minus 2 root AB is greater than 0, which indicates A plus B is greater than 2 root AB. That means root AB is less than A plus B by 2, which is the required identity that we wanted to prove. So, that is the arithmetic geometric mean inequality. Now, this can be extended to a general case where we have A1, A2, etc. An power 1 by n is less than or equal to the arithmetic mean of these numbers A1, A2, etc. up to An. So, that is also a generalization which can be proved by mathematical induction, of course. The next inequality is what is called the Bernoulli's inequality, which is a very important inequality in real analysis. If x is greater than minus 1, then 1 plus x power n is greater than or equal to 1 plus nx for all n element of capital N. That means for all natural numbers, if x is greater than negative 1, 1 plus x whole power n is greater than or equal to 1 plus nx. So, because it is true for all natural numbers, we will be proving it by mathematical induction itself. So, Bernoulli's inequality the proof follows from mathematical induction, and so we first consider the case when n is equal to 1. So, given x is greater than minus 1, what we require to prove is 1 plus x whole power n is greater than or equal to 1 plus nx, greater than or equal to 1 plus nx. So, first case when n is equal to 1, LHS is equal to 1 plus x, whereas RHS is equal to 1 plus 1 into x, which is again 1 plus x. So, we have LHS is equal to RHS. So, the case is true for n equal to 1. So, by mathematical induction, the hypothesis of mathematical induction, let the Bernoulli's inequality be true for some n equal to k. That means 1 plus x whole power k is greater than or equal to 1 plus kx for k greater than 1. For some natural number k which is greater than 1, let this condition be true. Now, consider the case when 1 plus x power k plus 1 is taken. So, we can split this into 2, namely what we have 1 plus x power k we have and 1 plus x. So, we can split this as a product of 1 plus x power k into 1 plus x. So, we can apply this inequality that we already have. So, this is greater than or equal to 1 plus kx into 1 plus x, which can be simplified as 1 plus x power k plus 1 is greater than or equal to 1 plus kx into 1 plus x, which is equal to, we can write 1 plus kx plus x plus kx square by multiplying these two using the distributive property that we have learned. So, what is these two terms added up together? We are having that is greater than or equal to 1 plus k plus 1 into x plus kx square, and since in the condition of the inequality itself it is given x is greater than negative 1, x square is definitely greater than 1, and therefore, k times x square is also greater than 1. So, kx square is greater than k we can write, which is definitely greater than 1, because our assumption is like that. So, this is strictly greater than 1 plus k plus 1 times x, because we are having some natural number or some real number which is greater than 1 added up to this. So, being an inequality, we can replace it by a still lower number. So, therefore, Bernoulli's inequality is satisfied. 1 plus x power n is greater than or equal to 1 plus nx for every natural number n. So, that completes the proof of Bernoulli's inequality. Okay. So, in today's session, what we have discussed so far is about inequalities and some problems using the algebraic and order properties of real numbers. Thank you.